Joan said, I'm going to talk about the science behind climate change and tell you what's really going on. My day job is working for a small company, Remote Sensing Systems, whose offices are actually located about 100 feet in that direction, so it was a very low carbon commute. And we specialize in processing data from weather satellites for various scientific purposes, and often for climate change detection and attribution and that sort of thing. Here we have some of the pictures of some of the satellites that we study. These guys go around the Earth in polar orbits, mostly, and they measure things like the temperature and the wind speed and that sort of thing. First, I thought I'd just give some basic climate science, just to get everyone on the same page. I realize you guys are probably mostly the choir, but at least thought I'd empower the choir to go out into the world. And then I'm going to talk about some recent climate myths that have been propagated through the media, and then give scientific rebuttals to these. And then at the very end, I'll talk a little bit about what might happen to Sonoma County in the long run. Okay, so anthropogenic climate change. That means the climate change that we, the humans, are causing. It's actually a very simple idea. Humans burn stuff and spew gases into the atmosphere. These gases make it harder for the Earth to get rid of the heat. The Earth warms up. That's it. No fancy equations. In fact, it's very similar to this system, which I call very local climate change. The basic idea here is you have a baby. The parent throws a blanket on the baby. This makes it harder for the baby to get rid of heat. The baby warms up. It's exactly the same system. Now, you'll notice over there I have some question marks. And that's because in order to determine exactly how hot the baby's going to get, you have to delve into the details a little bit. How wiggly is the baby? How thick is the blanket? Does the baby kick the blanket off? And this is really the crux of climate science. You have to, in order to really understand how much the Earth is going to warm for a given amount of greenhouse gas, you have to kind of get into the details. Okay. So the next level of detail is here. This is kind of a pictorial representation of the greenhouse effect. You have the sun up here. Radiation from the sun comes down, goes through the atmosphere. Some of it reflects off clouds, and some of it reflects off the surface, but about half of it gets absorbed by the surface, where it's converted into heat and infrared radiation, which goes back up. And if there were no greenhouse gases, that infrared radiation would go to space and the planet would cool off pretty rapidly. In fact, it would be, the average temperature would be much closer to 0 than it is to what it is now, about 60 degrees. Okay, so what are these greenhouse gases? Next slide. Here's some important greenhouse gases. Our favorite, carbon dioxide, water vapor, methane, and ozone. And this is my trick question tonight. Does anybody know which gas produces the largest greenhouse effect currently? Water vapor is actually the correct answer. However, water vapor is a little different than other ones because we don't control how much there is in the atmosphere. How much is in the atmosphere is just controlled by the temperature. If the air warms up, it can hold more water vapor. If it cools down, it can hold less. It turns to clouds and rains out. All right, next slide. Okay, there's a lot of other factors that can influence climate, and I'm going to show you a couple here. One is changes in the sun's output. The amount of energy that comes out of the sun goes up and down as time goes on in kind of a sort of a semi-11-year cycle. That can change the temperature of the Earth a tiny bit. And then every now and again you get a really big volcanic eruption, and that puts a lot of fine dust, or what we like to call aerosols. Though I realize that's confusing because it gets all in the aerosol cans and stuff. Let's just call it dust. It puts the dust into the atmosphere, and this can change the climate. You can get a direct cooling effect just because the dust gets in the way of the sun. And then also all those dust particles up there change the way the clouds form. And that's actually one of the most complicated things that we study and probably where a lot of the uncertainty is. Okay, next slide. Okay, so are we changing the composition of the atmosphere? I can answer this one easily. Certainly, yes. What I have here is a plot of the amount of carbon dioxide in the atmosphere starting at about 1960 and ending at about the year 2000. 1960 it was about 315 parts per million. By 2000 it's about 370, and now we're getting awfully close to 390. So the long-term trend in this is absolutely due to the emission of carbon dioxide due to fossil fuel burning. And one thing that I think is really cool is that each year it bounces up and down a little bit. And that's from the planet breathing. During the summer, in the northern hemisphere summer, you get lots of trees and plants growing. They make lots of new leaves, and they actually take some of the carbon dioxide out of the atmosphere. And then in the fall, when all those leaves fall off, they go back down to the ground, they decay, and they emit carbon dioxide. And so that's what's causing these wiggles. These wiggles are not noise or uncertainty or anything like that. Those are a real effect of the planet breathing. Okay? Okay, is the planet currently warming? My answer here is almost certainly yes. There's lots of evidence. Probably a lot of you have seen this evidence before. The temperature is increasing almost everywhere when you measure it with thermometers or satellites or however you measure it. The North Pole ice is melting rapidly. I'll get to that a little bit later. The springtime snow cover in places like northern Canada is decreasing. Various lakes and rivers melt earlier in the year. The sea level is increasing. And then the patterns of precipitation are changing, all over the globe. And there's a little bit of evidence that points the other way, but we mostly understand why that might happen. A few glaciers are actually increasing in size, but this is mostly in places where the precipitation is increasing, so you're getting more snow on top of the glacier, so that's getting converted into ice, which then flows down, makes the glacier bigger. And then in a few places, the temperatures are actually decreasing. And one such place is the South Pole, but this is understood to be mostly due to the loss of ozone, due to the ozone hole you might have heard about, and then also how that changes the weather surrounding the pole. Okay, now you get to the really important and somewhat harder to answer question. Is it our fault? My short answer is very likely yes, but I'm going to actually look at some evidence for this because I think this is something that a lot of the arguments are about, and there's some really strong evidence to suggest that we are. Okay, the hardest thing to figure out, we've seen that the Earth is warming and so on and so forth, but we have to figure out, is this due to natural causes, or is it actually due to the stuff that we're doing? And in order to do this, you have to really kind of delve into the climate system. And it's quite a complex system. So scientists tend to use climate models to help us understand what's going on. And the kind of model I'm going to talk about is what's called a general circulation model, where you try and basically model with a computer the weather over the entire Earth for hundreds of years. So this is sort of a schematic model of what, a schematic diagram of how the model works. What you do is you divide the Earth up into little squares, both north and south and east and west, and then also up and down in the atmosphere too. That's what that little red box is trying to depict there. And then in each one of those squares, you just apply basic physics. Now it includes things like F equals ma, conservation of mass, conservation of energy, which gets a little bit complicated because water is evaporating and condensing all the time. But anyway, you include all the basic things that you know about just from physics. Some of those are depicted here. And then you get a simulation of what the climate's going to do. Okay, worldwide, there's more than 20 different climate modeling centers who all have big supercomputers, and they run these climate models. And that's good, because you would never want to trust the output of this one climate model, because you don't know what kind of mistakes they made. But if you look at 20 different ones, and they all tell you more or less the same thing, then you're much more convinced. Okay, so what do the climate models predict? Well, I don't really have enough time to get into everything. But one thing the climate scientists like to talk about is what we call climate science sensitivity. And that is just a simple number. If we doubled the carbon dioxide, and then we waited a long time, how much would the temperature change? And the climate models currently predict between, if you did that, you'd get a temperature increase of between 1.5 and 4.5 degrees C, with most of them predicting an increase of about 3 degrees centigrade, or almost 6 degrees Fahrenheit, 5.5 degrees Fahrenheit. But if you're skeptical about things, and I count myself as a skeptic, I realize that word's kind of been appropriated by what I call contrarians. How do we know these models are right? So we actually test them a lot. And one of the things that we use to test them is actually, can they predict the past? So, it seems like kind of a funny thing to do. We already know what happened in the past, but it is an important test for the climate models. So what you do is you take the historical values that are measured for things like carbon dioxide, methane, whether or not volcanoes went off, and also the measured values of the solar output over the last century. And you stuff those all into the climate model, and then you see what it predicts, quote. Of course, it's all in the past. And then you compare those predictions with what really happened. Okay, so next slide. Okay, so this is what happens if you do a thing like that, except that you ignore the stuff that we've done to the atmosphere. Okay, this is kind of a complicated plot, so I'm going to walk you through it. Okay, this black line here is what really happened to the global average temperature measured with thermometers over the past 100 years. You can see that between 1900 and about 1940 it increased. Then it kind of maybe even cooled down a little bit for 20 years between 1940 and 1960. And then from then to the present, it started warming even faster. Okay, in this experiment, we took maybe 20 different climate models, and we asked them to do the simulation. And these thin little tiny blue lines that you can barely see are what each climate model predicted about the past. And then the thick blue line is what the climate model, what all of them averaged together predicted. And you can see that when you ignore the changes in the atmosphere due to carbon dioxide changes from us burning fossil fuels, or the changing in methane because we grow too much rice or have too many cows or whatever, you can see that you just cannot explain the rise in temperature after 1960. However, next slide, if you include the changes we've made to the atmosphere, and by this I mean carbon dioxide, methane, ozone, and so forth, and you run exactly the same experiment with exactly the same models, you get this result. Once again, the skinny yellow lines are the results from each individual model, and then the red line is all of them averaged together. And you can see you can actually explain what happened in the past relatively accurately. And to me, this is one of the most convincing things. The most convincing piece of evidence that we're the cause, because you can look into the past and use these models to try and predict what happened, and you cannot explain it in any way, shape, or form unless you include what we did to the atmosphere. So evidence like this led me to conclude in about 2008 that it seemed like the science was settled and we could just move on to trying to figure out what to do about this problem. However, this proved not to be the case. Starting in 2009, 2010, the attacks on the scientists and then on the science, and unfortunately on the scientists as well, have ramped up. And the people that are attacking, and I'll call them the contrarians, are tricky individuals. They often make statements that are true, but totally distort the context. And I'm going to go through some examples so you can see what I'm talking about. And so when you hear some of these arguments from your friends, you can point out where they're wrong. And one of the easiest ones to explain is Arctic sea ice extent. And what this is, scientists use satellite data, in fact they use the data from our company, to measure where the ice is in the Arctic. So what we have here is a map of the globe, and we're looking down from on top of the North Pole. And to help orient you, this big gray thing here is Greenland. Over here is Alaska. This is the Great Lakes here. And this kind of snake-like thing here is Norway and Sweden, which is about to bite the head off of Denmark. And this is some relatively recent data. It's actually from yesterday. From June 29, 2010, this is exactly where the ice was in the Arctic. And what generally happens is then during the spring and summer, it melts away. And then starting in about September, it reaches a minimum. And then in the fall, it spends all the following fall and winter freezing back again. So you kind of get this cyclic amount of sea ice. Let's go to the next slide. One of the things that we like to talk about is the amount of ice there is at the minimum at the end of the summer. And I want to point out that this is not a small effect, this melting of Arctic ice. increasing with climate change. So where it's white here in this picture is where the minimum ice was in 2007. And then this kind of bright green line here is where it usually is. So you can see that it's quite a bit smaller. It's about 2 million square kilometers smaller than usual. And I point out that's about 5 times the area of California. So we're talking a lot of ice. Okay, next slide. Okay, so what I'm doing in this plot, I'm kind of like condensing the information from the maps. So what I'm doing is plotting the area of the ice in the vertical axis as a function of time. And then once again, the black line is what's actually been happening. So, 1980, 1990, it was up here about where it's supposed to be, and then it started, each summer it melted more and more and more until we got to this 2007, where we had, the minimum, where we had the record low amount of ice in September. And then the next 2 years, it got a little bit better. And in fact, that's one of the things the contrarians like to do. They like to ignore all the data until 2007, and then just focus on this little bit of line right here, and they say, oh, the ice is coming back. But it's still much, much lower than it's supposed to be. And the other part of this plot is all these colored lines are the predictions of the various climate models. And you can see that we're actually typically having less ice than even the most pessimistic climate model. So this is the case where the change is happening even faster than we think it should. Okay, so let's look at the contrarian spin on this. Okay, next slide. Okay, this is the web page I found. Climate change fraud, makes me feel good. And then they're like claiming here that the liberal media is somehow ignoring the fact that the sea ice has come back. And in fact, sometime in late March of this year, so this is once again is the amount of sea ice in the vertical axis as a function of time, January, February, March. And then the blue is what actually happened this year, and the black is what's normal. And for like one fleeting instant in the middle of March, we actually got almost back to normal. And they expected us to tout this as, evidence that there's no more global warming. However, this ice here isn't very old, because it only froze in the previous month, so it's probably really thin, and it's probably going to melt really fast. Okay, let's see if that's the case. Let's look and see what really happened. This is the same plot, except we're going forward in time. Here's the point in March where we almost got to normal. And then you can see that as the spring started, here in May, it actually melted faster than it's ever melted before, and now we're way, way below normal. In fact, we're below the value for a record year in 2007. So it's possible we'll get another record low. And then to show you how these guys kind of spin stuff, this is the end of the previous plot, plotted by the contrarian. He ended his plot right when it was closest to the normal line. And this is the date he actually published it online about a month and a half later. You can see by then it was already starting to melt, but somehow he ignored that. And this happened basically, like I said, there was a lot of thin ice because the ice wasn't there very long. And also there were very, very warm temperatures in the Arctic this spring, about 2 degrees above normal. Okay, next. Okay, another thing that they like to shout about is they say no warming since 1998. And here's a BBC story, which if you read the whole story is actually fairly balanced. But the title is a little bit slanted. I mean, what happened to global warming, makes everybody think that if they just read the headline, they think, oh, it must be over, let's quit worrying about it. Okay, so let's look at this claim in a little bit more detail. Next slide. Okay, so this is the plot of the temperature, the average temperature of the air for the Earth, starting in 1979 and then going on to the present. And the time when they would really like to make this claim was in late 2008. And so what I did here is I just fitted a line to the time period from 1998 to 2008. And you can see that, in fact, well, it was cooling a little bit over that time period. But they did something kind of funny. They started their line, their fit, right here in this big hump right here, and then they ended it right where there was a big negative bump. makes me a little bit suspicious. So all these wiggles must be pretty important. So what are all those wiggles? Go to the next slide. So all the wiggles in this plot, not the overall warming up, but all the ups and downs that you see are due to El Nino events, or La Nina events, or volcanic eruptions. The red arrows are where we have El Ninos. You can see, here you got a bump up, El Nino. Here's a bump up, El Nino. Here's another one. And then here's a really big one. This is the biggest El Nino in recorded history in 97, 98. Remember, it rained like crazy. I remember skiing in June that year. And then we had another little El Nino in 2007, and we have a pretty big one going on right now. And then the blue arrows are La Ninas, and then the purple arrows are where we had big enough volcanic eruptions to actually cause something. And you can see that they tend to be associated with dips, so it's a little bit harder to see it. It's a lot easier to see the volcanic effects in the stratosphere. Okay, next slide. Okay, so their claim is true, in quotes. But it's only true if you get to cherry pick your time period. So I did the same experiment of fitting lines to 10-year sections of this plot, and you can see that every other time I did that, I got a positive trend. So in order to get that negative trend, you really have to pick your time period. And the real message here is that because of all these bumps up and down, 10 years is just too short of a time to have a meaningful discussion of climate change. You really need to look at 20 or 30 years before that signal is going to jump out above all the noise caused by the El Ninos and the La Ninas. Okay, next. Okay, this is my favorite. You might remember that in February, there was a big snowstorm in Washington, D.C. We had friends that were going to come out and visit, and they couldn't come because they were snowbound and so on and so forth. And then Senator Inhofe had his grandchildren build an igloo for Al Gore, in front of the Capitol or something like that, as if, he thought that a snowstorm in Washington somehow proved that global warming was over. But Washington is just one place. Let's look at the rest of the world and see what's going on. Okay, next slide. Okay, so this is a map of the entire world in February 2010. And this map is a map of the difference from normal for that month. So colors like red and yellow mean it was much, much warmer than normal. And colors like blue and purple mean it was much, much cooler than normal. And you can see, well, what do you know? On the East Coast, it was much, much cooler than normal. But most places, it was much, much warmer than normal. And including our favorite up here in the Canadian Arctic, where all that ice melted awfully fast. And that's probably because it's like 5 degrees above normal. And if you average over the whole Earth, you find that it was actually quite a bit above normal, almost an entire degree centigrade, so almost more than 1.5 degrees Fahrenheit. And it was the second warmest April on record. So one snowstorm in DC doesn't prove anything. And I also might add that one hurricane in New Orleans also does not prove anything. And we're sometimes guilty of the same thing when we're trying to convince people of climate change. One storm doesn't mean anything. Hundreds of storms might mean something. Okay, go on. Okay, so this is my synopsis of this part. We have a chart with the issues over here, the contrarian myth, and then what the real situation is, Arctic sea ice. The myth is, oh, the sea ice is recovering. And the real situation is this year, I think it really might reach another record low. And global temperature, they say, oh, no warming since 1998. Well, they're kind of true there, but the long-term warming is still happening, and they just happen to pick their endpoints just right to get a negative trend. And then snowstorms on the East Coast clearly prove that warming isn't happening. Wait, not. It's actually globally the second warmest February on record. Okay, so what's all this mean for Sonoma County? I kind of looked into this because I was kind of, interested in finding a way to communicate with local people. And the first thing I determined is that predicting the impact of global climate change on a local scale, like just Sonoma County, is much, much more difficult than predicting global things. And that's partly because not only you have to figure out what's going on with the temperature on a global scale, you're going to have to figure out whether more storms come or whether fewer storms come, whether it's going to rain more, and all these things are down in the details of the model, and they're actually not very good at doing that yet. However, I will present some results anyway, but you should take this with something of a grain of salt. because the predictions are much more uncertain than the global effects. So we use regional climate models to help predict what's going to happen more locally. And by a region, we mean North America. It's a pretty big region. And this is what the models predict a change might be by 2100 under a business as usual type scenario. And this is for all the different models combined together, so you don't have that problem with just one model saying something crazy. And you can see that, west coast of the United States, we're getting temperature increases of maybe 3-4 degrees. Oops, it doesn't seem that bad, but actually, I'll show you in a minute, it actually is pretty bad. And unfortunately, it doesn't look like much is going to happen to the precipitation at all. It's going to get much, much drier in the southwest and in Mexico, and much, much wetter in the Pacific Northwest. We're kind of in the middle of the seesaw. So it probably won't change that much. Maybe the rain will become more intense, but it's not going to be a huge drought. So I should definitely caveat any precipitation predictions, because that is exactly the kind of thing the models aren't so good at, because they don't, steering exactly where telling exactly where the storms are going to end up and that sort of thing is something that's much more uncertain. Okay, so I thought, well, what's this temperature change actually mean for Sonoma County? Something that I drive around out there, I see a lot of grapevines. I kind of wondered what the effects on the grapes might be. Okay, as the summers become hotter, it actually becomes quite a bit more difficult to grow premium grapes in Sonoma County. And there was a study published in the Proceedings in the National Academy of Sciences, which is a very reputable journal, where they did a study. And they used climate models to try and predict both where the good grape growing regions are now and also where they will be at the end of the century under a business as usual type scenario. Now, another caveat is these results are all from a single climate model, and I would be more convinced of the results if the author said use more than one, so we could see how much difference there is in between them. But let's go ahead anyway. Okay, so first they tried to figure out where grapes would grow well under the present climate. And so they used the climate from 1961 to 1989, sort of before global warming really got going. And this is a map of where you might try and grow grapes based on just temperature. It doesn't include humidity and precipitation and all that sort of thing. They just figured out how many years out of 25 would be good years based on temperature. And on this map, red colors means good for grapes, blue colors means bad for grapes, and white means you have no hope whatsoever. And you can see that in California, they actually did a pretty good job. There's lots of good grape growing regions around the Bay Area. Down near Santa Barbara, Paso Robles, that area, up through the Sierra foothills. So basically it's all the places where we're growing premium grapes currently. And then also, there's some up here in the Willamette Valley. And I'm not sure, I haven't heard of a big grape growing industry in Arizona, so it may be something with the humidity that makes it. And I did some research. I actually did find there are a few vineyards in North Carolina, but there's only 1,300 acres planted, and I think that's probably about 1% was planted in Sonoma County alone. But in California, I think the simulation did a pretty good job. Okay, so let's see what they predict in, at the end of the century, in 2080. So this is over the time period from 2071 to 2099. Same sort of map, red good, blue bad, white hopeless. And you can see that all the grapes in California are now, it's only possible in this really narrow band right along the coast, and it's basically all the places where right now are covered in redwoods. All the grape, there's lots up in the coastal hills of Oregon and Washington looks pretty good, except, as we saw a few slides ago, it's going to start raining really hard there, so it might not work so well. And then all that stuff in Appalachia is too hot too now. So this is, if I were a grape farmer, I'd be pretty frightened. All right, next slide. Okay, so in summary, climate change is still happening, and it's our fault. When you hear something on the radio, or on those awful Sunday morning talk shows, and someone's saying that we don't have to worry about it anymore, listen carefully to what they're saying, because those guys are tricky, and they'll make arguments that seem convincing, but if you look at the details, they just don't really hold water. And then the local impact will be significant, and it appears that it's mostly going to be temperature, not so much precipitation. And we considered having a whole list of websites you could go to for more information, but I looked at them all, and I realized that my favorite, Real Climate, was actually the best one, and then they actually have a link there that links to all the other ones. So if you want to find out more about the science from scientists, go to www.realclimate.org. Okay, that's it. Any questions?